k. Whenever I have a degree of k minus 1, in time it will sprout a link and get recruited into the k degree node class. And whenever I have node of degree k, it will sprout a link and then it will move out of the class. So this will be the gain term in this equation, that's the loss term. And when you solve this, this is just a Poisson degree distribution. You can just substitute it and find out, you can guess. And so this is how you use a differential equation. The other really simple but extremely important tool we use is the generating function. A generating function is a power series with the coefficient of z to the k, or the coefficients encode the sequence of interest. In this case, it's the degree distribution. So z to the 0 is accompanied by n0, the number of 0 degree nodes, and so on. It's really useful. As you can see, if you differentiate this, you get a power, you get 2 out, and then when you put z equals 1, you get the first moment or the average degree. If you differentiate it a times, you get some function of the 8th moment. I mean, this notation is for a falling factorial. This is like k times k minus 1, k minus 2, a of those terms. So you can extract higher moments. And obviously, this is useful because most of the times the generating function, even though it's an infinite summation, reduces to something really simple. So this is the Poisson degree distribution, and you get this is the generating function. You can calculate all kinds of things with this function. One small demonstration of what you can do with the generating function. A giant component of the network is the largest component which is connected. And it's specifically called the giant component if the largest component scales up with the size of the system, or the largest component is the macroscopic fraction of the whole system. So that's a giant component. So there's this really neat way of calculating the size of the giant component using the generating function. You see the probability that a node belongs to the giant component is if at least one of his friends belong to the giant component, and you sort of write a self-consistent equation. At least one of the friends is 1 minus probability that none of his friends are in the giant component. If he has no friends, then he's not in the giant component, he's just an isolated node. If he has one friend, then he does not belong to the giant component if his single friend does not belong to the giant component. And if he has two friends, both of them don't belong to the giant component. And you realize that this is conveniently just g of 1 minus p. And we already calculated g for the Poisson degree distribution, and you can get conveniently that the giant component is solution of this equation. Most of the times you get some really such simple reduction using the generating function. You can also get the component size distribution using the generating function. So the generating function of the component sizes, component or the cluster sizes, the connected component sizes, will be another self-consistent equation. The size of a component will be the probability. Okay, you can have a component of size 1. It is the same as having nodes of degree 0. They are isolated nodes. If you have degree 1, then the size of the component is 1 plus whatever the size of the component you are attached to. So you get z, which is counting this one node, times h of z, which is counting the distribution of this component size. And if you have two components, then you do that, and so on. I cheated a little bit here. Here, you have to be careful in counting. Oh, let me just finish the story. So this reduces to that. You realize that this is just the generating function for the degree. So the generating function for the cluster size distribution is connected to generating function of the degree distribution in a simple fashion. Although we have to be a little careful. This is not the same degree distribution, generating function we saw earlier. You have to be careful in general if you sample the node, you sample the vertices uniformly, or you sample an edge uniformly and then traverse that edge and reach a node. These are slightly different distributions. So in general, you have to be a little careful with this. Anyway, so now I have sufficiently motivated the two tools that I'll be using. Yeah.
That previous one, that was, what do you mean component size distribution?
Oh,
It's if you pick a node at random, it's the expected size of the component it's in?
that is correct.
Okay.
It will be the size of these blobs, basically. I didn't color all of them, but, there are so many one-sized components and, the distribution of connected clusters of nodes. That's right. When you sample nodes uniformly.
Okay.
Right. So, right. So, any questions at this? These are the only tools, and now I'll just, I'll just advertise the results of our models. All right. So, the copying model, it's a collaboration with Paul from BU, Sid, who's here, and René Lamierde from University of Namur. This is like a long project. We, every now and then we come across some neat properties and then get motivated to study and then sort of give up in the end. But let me just share with you the really cool results. So the model is as follows. So, okay, as a function of time, every time step you have an incoming node shown in orange. He connects to a node at random, let's call him the host node. And then he connects to his friends independently with a particular probability, say P1. And then friends of those thus connected friends with probability P2. And so on. You can extrapolate this to any extent. To begin with, let's just look at the first shell that you just connect with friends with probability P1. As I said, it's independent attachment. So 1 minus P square, you don't connect to his friends in this case. And P times 1 minus P, you connect to one of them. And P square, you connect to both of them. That's a binomial distribution of at each instance. The total number of links is counted as follows. So when the n plus 1th node appears, the total number of links is equal to the node links that were present plus the one connection with the host node plus on an average P times the average degree connections with his friends. The average degree, like I told you earlier, is 2 times L divided by N, so P times that. So this is the equation that counts the total number of links. This reduces to a differential equation when you do a large N assumption. And I mean, the surprisingly simple differential equation gives 3 regions of solutions. You can just substitute and try it out. So if P is small enough that the probability you connect to the friends is small enough, less than a half, you have linear increase in the number of links. And P larger than 1, you have a superlinear increase in the number of links. You can get the coefficients by solving the actual difference equation. And not only that, you can also count the total number of triangles and square fully complete motifs. And you get this series of transitions. So links until a half is linear in n, then becomes superlinear in n. Triangles is linear in the number of links, the previous motif, until 2/3 becomes superlinear in the number of links. Squares, fully complete squares, linear in triangles, superlinear, and so on. So even though the initial rules were so simple, there is this remarkable structure. And like I said, now whenever you see some such feature that, you vary a parameter, you see this linear region and then this superlinear region in your model, you immediately know probably it's because of the copying process. Then you will give me a phone call and, we'll collaborate on something. Anyways. So these are the kind of features. So these were the point estimates, or the total number of links. You can do it with more careful counting for the whole degree distribution. So now this is capital N, counting the total number of nodes with degree k. So the degree k is recruiting from k minus 1 degree nodes from the host nodes. And if the host node has degree k, then you lose a degree k vertex. From the friends, so each friend who is degree k has k minus 1 other friends, so you could reach to him with this multiplicative factor. So the recruitment from these friend shell is as seen here with the multiplicative factor of k and with probability p. And then you count the incoming node has degree k if he connects to a host node with sufficient number of friends and connects to at least to exactly k minus 1 of his friends. And this is like a full degree distribution equation with n dependence. So at first you can do a sparse approximation, say that this capital N of k, the total k degree nodes, is just n times small n of k, and then you can get this asymptotic tail. But you can also calculate all the moments if you have sufficient patience and want to do algebra in both the sparse region where it's finite and in the dense region where the moments grow. In fact, every higher moment grows earlier and earlier than p equals a half because of the asymptotic power law tail. How exactly does the distribution, the degree distribution converge to this asymptotic tail? This is just to get a flavor. In this case, it's an extremely slow convergence. So the axis is just the number of fraction of nodes of degree k versus the degree k. And the lightest is a network of size 100 going up to network of size 10 to the 8, the black curve. And you see that it's slowly converging to this asymptotic tail. So it's very easy to get confused by looking at a small network that probably it's not a power law, but maybe in the asymptotic region it can get power law. So there are all these finite size effects that are really interesting. That was in the sparse region. The dense region, we pretty much have no idea what's going on. We can solve numerically the degree distribution equation, but it's extremely tedious. You can do it up to like n to the 4 or 10 to the 4 or something. It seems the degree distribution converges to a log normal, and we can justify that because there are a lot of multiplicative processes that's happening. But we pretty much have no idea. I'm just saying stuff now. Let me skip. I mean, you can basically do same kind of careful calculations. In the sparse region, you can calculate the distance distributions, and this is just a simulation exercise. In the dense region, we don't really know what's happening. This is a little cryptic curve. So let me just give the message of this curve. It seems that in the dense region, the average distance tends to a constant, somewhere between 2 and 3, independent of the size of the network. How much time have I got? I think sufficient time.
No, 10 minutes.
Oh, okay. So now let's go to the second. Any questions at this point about the simpler copying model? Okay, so let's go to a slightly complicated model where we have the second shell also. So now we have P1, the property that you attach to the friend of the host node is P, friend of the host node, P square, but everything else is 0. We just extended it one more shell. Something really strange happens. For these values of P, you see that the total number of links seems to be growing like some power of n, but then suddenly starts avalanching. And if this curve is representative, it will eventually be an almost fully connected network. So the lines to guide your eye, this is a fully connected network. Total number of links is n squared by 2, and this is just L equals n. So that's really curious. And for smaller and smaller values of P, this transition point can be astronomically far. Maybe you would never see it in a real network. So what we did is you can write really carefully the formula for getting a fully connected network right from the beginning. Every node that comes into the network connects to everybody else. And we see that that's always finite, which means that finite fraction of the realization go to fully connected networks. But that's not what we see here. I mean, none of these realizations fall in this fraction of networks that became fully connected, because in the initial stages, some of the links were not connected. So what's the real quantity of interest is what fraction of the networks goes to almost fully connection, and that's something we are still trying to figure out.
I'm still a little confused about the model. What's the very first step? You introduce a new node.
So we begin with a single node. So, okay, we have just a single node to begin with, and we have nodes incoming at a constant rate. The node comes in, selects a random node from the population, connects to him. Definitely connects to him, yes.
And then your original model was, and then he might connect to some of the friends, and then you stop.
Right, yeah.
And this one is, he might connect to some of the friends, and then he might, with a different probability, connect to some of those friends, and then
right.
you stop.
Exactly,
Okay.
yeah. Sure.
When is
Oh, yeah, because you're copying the friends of the host node. Yeah, exactly. So, I mean, Sid and Paul had studied a similar model, but a simpler model earlier, where you connect to a host node, and then with probability P, you connect to all of his friends. You copy all of his, the host node, and with certain 1 minus P, you do not. Here, yeah, we are doing independently with each friend. So yeah, with the second shell, it seems like there is always this runaway effect, and eventually the network will become almost fully connected, no matter how small the probabilities P1 and P2 are. And you can understand this. Let me give an intuition why this happens. This is because when a network is really large, what will happen is there will be this one motif that's very dense, say 100 nodes within them, and then every node connected to a host node within this will be compelled to connect to all of them, because in the first shell, he connects to, say, 30 of the 100 nodes, but then he'll be introduced to the rest of the 70 multiple times. All these 30 people will be introducing him multiple times. So it becomes increasingly impossible that he does not connect. So, I mean, it's sort of the artifact of the detailed rules of the model. In reality, there will be some saturation effect or something that will kill off this avalanche. But, you know, if you follow the rules faithfully, you will eventually get an avalanche. Another model I'm working with Monique here and Laurent, who is a postdoc here, is a static version. So what we saw was like the dynamic version, which gives a lot of triangles. So here is a static version. You begin with an Erdős-Rényi, a random graph substrate with, say, average degree C. And then you complete the triangles or incomplete triangles with some fixed probability Q. The degree distribution is not that surprising. It's just got Gaussian tails. You can write, it's actually just a convolution of Poisson distributions. You can write the generating function, etc. But what's really interesting in this is the K-core structure. So for people who haven't heard about K-cores, let me explain what a 3-core is. A 3-core is the maximal subgraph of the network, such that everybody within the subgraph have degree 3 within themselves. For example, this node has degree 3, but it's not within. I mean, if I include this, you have to leave the subgraph to have degree 3. I mean, let me put it in other words, in an algorithmic way, how people find K-cores. You find K-cores by what is known as the trimming process. You trim away all the light nodes or degree 1 and 2 nodes. And when you do that, you have more induced light or degree 1 or 2 nodes. You trim away that too. You do this iteratively till it's no longer possible. So whatever's left is the 3-core. For K-core, it's just you do it till degree K. And for the ER random graph, the K-core structures are as follows. As you increase the average degree, so okay, you do this trimming process and whatever's left might still be disconnected. And then you find the giant component within that, right? What is the largest connected K-core? The 1 core is just the giant component we talked about, just a connected component. 2 core is some fraction of that. It's not that interesting. 3 core, however, shows this discontinuous transition. So what really happens is, as you get closer and closer to these points, there are all these tiny 3 cores that are not connected to each other. And at exactly this point, you sort of get this macroscopic fraction of a 3-core giant component. What happens with this, that was for just the ER random graph. What happens with this addition of this completion of triangles, this is a really busy slide, but kind of colorful. What happens is the sharp transition, just follow this line, which was for just the pure Erdős-Rényi random graph, sort of smoothens out. So let me explain this super busy graph. This is the same as the plot before, the size of the 3-core giant component. C is the average degree of the Erdős-Rényi substrate. And the individual curves are for different probabilities of completion of triangles. So if Q equals 1, you connect every triangle that was there in the substrate. And you see that it actually becomes a second order transition. As you reduce Q, it slowly shifts through, and we're still trying to pinpoint what kind of transitions these are. And for really tiny Q, then you see that the first order transition emerges, and then you go back to this. Now, there are many things happening in this. So you're completing the triangles, but you're also sort of morphing the degree distribution. You're making it wider and you're changing the average degree. For starters, the average degree is not that driving the 3-core component emerging. So what we did next is, like we found the simple giant component for the ER random graph, you can do the same thing to find giant 3 cores, and this is nicely outlined in this paper. You can write the generating function. Let me tell you how it's done mechanistically. Our node belongs to a 3-core giant component if at least 3 of his friends belong to the giant component. And these 3 nodes belong to the giant component if at least 2 of their friends are in the giant component, because the parent obviously is in the giant component. You sort of write 2 self-consistent equations, one for the original node and one for subsequent nodes. And then this is the same plot as before, but the solid lines are the analytical solutions following that. Notice that this does not capture the degree-degree correlations or the number of triangles. This just captures the morphing of the degree distribution. So we still have a lot of explaining to do why this difference occurs, and these lines are always showing a first order transition, whereas the original process does not show that everywhere. So a lot of cool things. So whenever you see 3 cores emerging continuously, you can guess this is probably because of some sort of triangle completion that's happening. What's in the future? We need to develop better tools for analyzing growing networks. There are many other important quantities. I just talked about the giant component, or the K-core, which is the trimmed down giant component, and degree distribution. But there are many other important quantities that people are interested in, and compared with real data, so that for the next talk I have a super awesome motivation. I put up some real picture of a real network or something. Some really good references. This is like a Bible of generating functions. It's a 20-page paper that really with a lot of detail, explains how generating functions work in networks in particular. This is a paper I mentioned before, which tells you how to calculate 3-cores, K-core structures. This is the earlier paper with the simpler copying model, and this is another paper where we are more realistic about the rules and trying to follow a Facebook model, put thresholds when people form friends and such. And this is a really good textbook for using master equations and generating functions in general. All right, any questions?